The following is a video clip from the webcast, 4 Ways to Boost Simulation Data Processing Using Python. In this segment, Matt Ozalas talks about directly comparing simulation with measurement by using a Pyvisa interface. Here, Matt shows an example of putting simulation data on a DCA oscilloscope for a PAM-4 waveform.
All right, so in the last example, we took measured data, brought it into the simulator, and processed it in the simulator. In this example, we're going to do the exact opposite. We're going to take a simulation and send it over to an oscilloscope to process the simulation data on the oscilloscope. And the reason for that is a lot of times these days we've got a function in the simulation tool. Let's say it's to generate an eye diagram, and there's a function in the oscilloscope to generate an eye diagram. And it's hard to tell whether those functions are consistent or not. Probably they're not. But if you look at test equipment these days, a lot of them have some pretty advanced functionality on them. So more and more, I think it makes sense to take a simulated set of data and put it in a piece of test equipment and actually do data processing over there. So this example, I'm going to kind of switch gears off the power amplifier track a little bit, and we'll talk about a modulated waveform. In this case, I'm going to focus on a PAM-4 waveform. So this is a pulsed amplitude modulation, 4 levels, and these signals have high data rates because for each clock cycle you can transmit 2 bits. But the problem is there's 4 logic levels now. So if you think about a standard eye diagram, the eye diagram for PAM-4 will actually split into 3. So you'll have 3 eyes instead of 1. And as you might guess from that, when you send it through any kind of channel, the noise and distortion requirements are going to get pretty challenging. It's going to be a lot easier to close 1/3 of the eye diagram than it is to close the entire eye. So one thing that's really necessary to do for these types of signals is the channel simulation. So channel simulation is where you take this signal and send it through some type of physical medium, whatever that is, whether it's a cable or a board or anything. And the reality is channel simulation, correlating that with measurement, there's a lot of reasons why this is a difficult exercise. And so what we zeroed in on, I'm kind of basing this work on a paper that a few of my colleagues did, and they said, okay, instead of trying to do something for a very, very complicated system, let's focus in on a relatively simple test case. Let's just take a length of cable and see what kind of obstacles we hit when we're trying to correlate simulation to measurement. What do we run into? What are the challenges that we hit here? And one of the things that came up, I guess, and this is the setup that I'm showing before I get to that, the beauty of this type of setup, we're just going to run it through a 3-meter length of cable. Well, you can take the same waveform from the simulation environment and you can put it over on the waveform generator. I mean, I'm simplifying this a little bit. Or you can take a measurement of the cable, which we do, and use it directly in the simulation. So these things really should line up. There's no reason that these 2 signals shouldn't agree pretty well. But it turns out when you dig in a little bit, there are a number of reasons why it's challenging. And one of the reasons is that we could have differences in signal processing on an oscilloscope versus in our simulation data display. So, for example, I could have exactly the same waveform in my simulation environment and run it through a function to generate an eye diagram and return the logic levels, and I could have the same waveform on the exact same waveform, try to do the same thing, and I'd get a different result because of the filtering and maybe the noise injection and things like that. So the goal for this exercise is really to eliminate that uncertainty for this PAM-4 eye diagram by loading the simulation result into the same oscilloscope that we use to do the measurement. And that way both waveforms are processed in the same manner. So before I get into that, I want to just talk about how this is enabled. I mean, how do I do this in the first place? And the way I do is I use this package called Pyvisa in Python, and this package just allows me to basically connect Python to my measurement test equipment and start sending Skippy commands. So this is something that's not included directly with Anaconda. You'll have to add it on, but it's pretty simple to do. And the other thing is that you've got to have the I/O libraries installed. So for Keysight equipment, you can find the I/O libraries for your instruments here. But if you have the I/O libraries installed and you have everything configured and Pyvisa package installed, then you can just easily send Skippy commands to your instruments through Python. And the way to do it is import Visa, so that's the package, and then here I open up the oscilloscope. In this case, I'm using the 86100D DCA X oscilloscope from Keysight, and I can also just use the software for that oscilloscope as well. So for this demo, I'll use the Flex DCA software. But basically, it performs in exactly the same manner. I open the instrument, and then I can write the instrument, I can read from the instrument, I can query it. So in this case, from Python, when I do that, I query the identity, I get the instrument name back that prints out to the command line in Python. And if you want to find out more information about the Flex DCA, you can find that at the link here. Okay, so now let's talk about how to implement this. Basically, we're going to have our measurement here, and that's going to be connected into the oscilloscope, so we'll have a measured waveform sitting there. And then we're going to run a simulation in ADS, and the simulation is going to generate a CSV file. That's going to happen kind of after the simulation completes. We're going to build a CSV file with the data. Now, we're going to also invoke Python in that, and we'll pass the waveform file name, so we'll pass the path of this CSV file to the instrument, to Python, and we'll also pass in some measurement specs. And Python is going to go configure the instrument to do an eye diagram measurement. So there's probably about 70 lines, 60 or 70 lines of Skippy commands that I do to configure the instrument. And then it's going to measure, so we're going to get both simulation and measurement waveforms on there, and we'll measure the levels for the simulation and measurement. And then we're going to take the data and return those levels back to ADS. That's all going to happen in one step after the simulation is completed. And again, this is really ensuring that both simulated and measured waveforms are processed and measured in exactly the same manner. Okay, so let me share my screen here. So first I'll show you kind of the channel simulation that we're running. So here's the waveform. We run it through this measure 3 meters of cable, and this is just a pass-through receiver, so this just converts the signal, the differential signal to signal ended, and it doesn't do anything else to the data. So we run this channel simulation. Now this takes a couple of minutes to run, so I'm not going to be able to do that in real time here, but the result is basically a data set, and we write a waveform from that. Now over here, I've got the Flex DCA. And again, this is just the software for the Flex DCA oscilloscope. It's exactly the same as the front end you'd see on the oscilloscope. And in the simulation, I'm going to invoke a Python script called Flex DCA, and then I'll pass in like the instrument address, I'll tell it where the waveform is, and then I'll give it some measurement specs, the delays and the sample rates. And that's going to run. You're actually going to see the Flex DCA go under local control once Python takes over. And you're going to see the instrument will go into an eye diagram mode, the simulation data will get loaded on top of the measurement, and then the levels will get returned all in one step once I invoke the script. So let's do that. So I'm going to invoke the script here. You'll see the instrument will go under local control. There's the eye diagrams, there's the levels, and then they get returned back to the simulation tool. Now the really nice thing over on the Flex DCA, I can even make a visual comparison of the simulated and measured waveform. So I need to go under local control to get back control over the Skippy line. So you can see here that when I loaded the simulated signal onto the measurement, the delays were a little bit different. I mean, that's a pretty common thing to have happen. So one other capability that I've got here is I can fine-tune something like time delay right out of the simulator. And the way I do it is just, I've got in my library, in my AEL Python data link library, the ability to send Skippy commands right out of ADS. So there's functions in there that invoke the Python in the background, and that allows me to write Skippy commands to the instrument. So when I do this, I can use a marker, for example, to adjust the time delay on the signal. So as I move this marker, you can see the simulation waveform is changing. And so anyway, as expected, the simulation and measurement agree pretty well.